Having described the process of radiation emission, the mechanism via which some object that has some thermal properties will continuously emit electromagnetic energy in the form of light into the space that surrounds it, it now makes sense for us to consider the other side of the coin of this mysterious process we called radiation. The mechanism via which electromagnetic energy, light that's floating around in space, interacts with matter and is then converted into thermal energy or heat. And the mechanism that we're going to use to characterize this process, which we had called absorption, is not going to be much more complex or difficult than the way that we characterized emission. The only thing that we have to do is to account for a couple of extra bells and whistles associated with the fact that there's more than one thing that light can do when it interacts with matter. So what is the conceptual setup for this kind of, idea for the notion of light interacting with matter? Well, let's suppose that you have some beam of light that has some energy flux Q double prime I, and then that beam of light hits a specific point on the surface of an object. Well, how do we characterize this beam of light? Well, it's easy to try to just say, okay, well, we have some energy flux, some electromagnetic energy flux Q double prime I incident on that specific point of the surface. But just like we found for emission, it turns out that we have to account for a bunch of different things that could affect that energy flux. In particular, we have to account for the way that direction and wavelength affect the properties of this beam. And so rather than actually considering pure electromagnetic energy fluxes, what we do is that we consider this sort of incident spectral intensity, which accounts for basically this energy flux per solid angle, per direction and per wavelength. And when we integrate this incident spectral intensity over all possible directions and all possible wavelengths, we find that net electromagnetic energy flux, Q double prime I. In the same way that when we integrated the emitted spectral intensity over all directions and wavelengths, we found the emitted energy flux. And so it's the exact same integral, it's the exact same concept, except that now, rather than thinking about that beam leaving a point on the surface of an object, we're thinking about that beam entering the surface. All right? So what does it do once it actually hits the surface? Well, there are three different things that we assume that light can do once it actually interacts with matter. The first thing that it can do, which is perhaps the most obvious, at least in the context of this course, is that it can get absorbed, that electromagnetic energy flux becomes converted into a heat flux because the matter absorbs that light and then takes its energy and converts it into thermal energy. But that's not the only thing that can happen. That beam of light can also be reflected, right? It impacts the surface, and because of the properties of the beam of light or the properties of matter, that light maybe just doesn't become absorbed by the object and is bounced off, so to speak, out back into space. And then the other thing that could occur, in addition to absorption and reflection, is transmission, which is simply that the object does not interact with the light at all. And so the light passes harmlessly through the object in what we usually call transmission. Now, it seems a little bit weird to use the word transmission in this context. It feels like transmission is like an active thing, like we say that we transmit radio waves. But in this context, it's a passive thing. It's just the process via which light harmlessly passes through an object without interacting with it. And so we might say, for example, that glass, like clear glass that we use for our windows, is a good transmitter of visible light because most visible light goes straight through it. It doesn't get absorbed or it doesn't get reflected. So each of these processes has a very important role in the way that we interact with light in our day-to-day. Of course, transmission, as you now know, is responsible for the fact that glass allows light to come in to buildings. But we also find, for example, that transmission is very important because we tend to be very good transmitters of radio waves. Radio waves have such a large wavelength that we usually don't tend to interact very much with them. And so the communications network that is built off of the notion of radio waves in our modern world is not hampered by the fact that all of those radio waves are continuously interacting with our bodies, right? They usually just go straight through them. Our bodies transmit them. Reflection also plays an important role, reflection. It plays a particularly important role in the notion of coloring, right? So I'm wearing an orange shirt right now. And the reason that you see this shirt as being orange is because the white light that is coming in and impacting my shirt, some of it is being absorbed. Not a lot of it is being transmitted, but I suppose some of the really large wavelength stuff is being transmitted. Most of it gets absorbed, but then the light that is at the wavelength associated with the color orange is reflected. And so even though the light that's incident on my shirt has wavelengths that are consistent with white light, the light that is reflected off has wavelengths which are consistent with a roughly orange color, which means that when that light reaches your eyeballs, you observe that my shirt appears orange because the light that is reflected off of it is orange. And so, of course, this plays a huge role in the way that we design or characterize things. It plays a huge role in what shirt I decided to pick for this lecture this morning. And so reflection is an important piece too. But from the perspective of heat transfer, the thing that we care the most about is, of course, absorption. And the way that we characterize all three of these things is by simply considering ratios. So we can consider how much of that incident electromagnetic energy flux right here, how much of that is being absorbed and how much of it is being transmitted and how much of it is being reflected. And what we'll find if we do that is that we can characterize each of these processes by a ratio that tells us how much is being absorbed or reflected or transmitted relative to the net amount of electromagnetic energy flux that's actually incident on the surface. All right? And so we create these ratios the same way that we created an emissivity. We can create these ratios called the absorptivity, the transmittivity, and the reflectivity respectively that tell us how much of this energy flux is absorbed or transmitted or reflected. And so, of course, the heat flux, the actual quantity that we use for calculating things in the context of heat transfer, is simply that incident electromagnetic energy flux multiplied by the absorptivity of the material. So we take all of these things to be a property of the material, but they're also a property of things like, for example, the wavelength, right? The reflectivity of my shirt clearly has to be a function of the wavelength of light, because if not, it wouldn't be able to generate the color orange, right? The color orange wouldn't dominate in the wavelengths of light that are reflected off of it. And so we expect that these properties are, in a similar way to the emissivity, they contain a lot of the complicated physics that we don't want to model from the perspective, at least, of this course. Nevertheless, there are a couple of things that we can say about them. And the thing that we can say about them, of course, is that if we assume that these are the only three things that can happen to light, then the sum of all of these ratios has to be 1. Okay? And that's really useful because if we know the absorptivity and the reflectivity of an object, then we can figure out its transmittivity or, other things. And so having described these three properties, let me tell you a little bit more about the vocabulary that people use to characterize the absorptive properties, or I guess the properties of an object, the properties of some chunk of matter as it relates to its interaction with light. And one of the vocabulary words that people like to use when describing objects in this context is opaque. And all that opaque means in the context of what we're talking about is that we assume that the transmittivity of the object is 0. Now, this is never true for all objects in all wavelengths, right? Of course, for example, the human body is a very good absorber of infrared, but we are very good transmitters of radio waves, which means that the transmittivity that we have at wavelengths associated with radio waves is probably going to be a significant, very, very close to 1. It's not 0 at all. Nevertheless, what winds up happening is that for particularly narrow bands of wavelengths, where we may prefer to focus our attention on when it comes to radiation problems, we find that this opaqueness assumption might work. So if we're working with bands of wavelengths that are, roughly in the infrared, then we can make the opaque assumption for, say, the human body. And just to clarify something, I don't want to mislead you, the radio waves that we are transparent to usually tend to have very, very large frequencies, okay? So not necessarily the radio wavelengths that we would associate with like radio communication. But just remember that radio waves are anything that has a a wavelength of 10 to the 3 meters or larger. So just making sure I don't mislead you into thinking something incorrect. So that describes opaqueness. The other property that I want to describe is grayness. And this is a weird one to think about because it's actually more of an emission property. The reason that I mention it in this lecture and not the previous one is because of the fact that it has a very significant effect on the way that we can assume or model the process of absorption. And grayness just means that the emitted spectral intensity of the object is approximately independent of the wavelength. That is to say that any emissions that are generated by an object, all of that electromagnetic energy, that the object has no preference. It generates electromagnetic energy at large wavelengths, the same amount that it generates energy at small wavelengths, and so on. And this can't quite be true, right? Because if that were the case, it means that it's emitting a non-negligible amount of gamma rays, which means that anybody who experiments with the object will get destroyed, completely obliterated. But once again, just like for opaqueness, as long as we're working with a narrow band of wavelengths, as long as we only care about a narrow band, we can make this gray assumption. And the reason that this matters is because if we make this assumption, it, by extension, implies that the emissivity of the object is the same as the absorptivity, okay? And that's great because right now, right, we can consider that we have 4 material properties that relate to radiation: absorptivity, reflectivity, transmittivity, and emissivity. But if we assume that an object is opaque, that gets rid of one, right? That fixes the value of the transmittivity. And if we assume that the object is gray, then that gets rid of another, because now the absorptivity is the same as the emissivity, which lets us work with only 2 independent parameters rather than 4. And the whole idea is that whenever we're thinking about the process of the absorption of radiation, the only thing that we have to account for from the perspective of actually, modeling it is this material property that we've called the absorptivity, and then the dependence of the absorptivity on wavelength, and then also the not material properties, but the properties of the actual incident electromagnetic radiation that is impacting the surface of the object. And then once we know what those properties are, we can finally obtain a heat flux. We can finally obtain a value that we can use for heat transfer calculations. Now, it'll turn out, as we will discuss in the next lecture, that the process in which we do this will be significantly more complex than in conduction or convection. And the reason for this actually doesn't have to do with any complications involving these triple integrals or with anything that involves the process in which radiation is emitted or absorbed directly. It actually has to do with geometry, but we will see that in the next lecture.